video I'm going to talk about second order linear differential equations that have complex roots in preparation for talking about second order linear recurrence relations with complex roots. So if you recall, there are three situations for the characteristic equation for differential equations, and this is the same for recurrence relations. You can either have two distinct real roots, which is the usual case, or you can have one repeated real root, and this is the case where you end up having to multiply the solution by n to get your complete set of solutions. I've already addressed this in earlier videos, but now I want to look at the third case where the characteristic equation has two complex roots. And it's always going to be the case when you have complex roots that one will be the complex conjugate of the other. And so if you don't know what that means, it means that you have this real part, which I'm calling alpha, and an imaginary part, which I'm calling beta. And one root is going to be alpha plus I beta, and the other one is just going to be alpha minus I beta. That comes from the quadratic formula. You have like that plus or minus sign in there before the square root thing. So, okay, so let's look at this. This is Euler's formula right here. I'm also going to assume that you already kind of know why this is. I don't want to go too in depth with this. But what you can do is if you multiply both sides by r, then what you can get is you end up being able to reach every point on the complex plane. And so I'll draw a picture of what I mean by that. So I'll call this the real axis and this the imaginary axis. This is the complex plane. I can draw a point here which I call alpha plus beta, or alpha plus I beta, and what that means is that the real component here is alpha and the imaginary part is beta. And so what I can do is think of this whole thing here as being alpha and this as being beta. And Euler's formula tells us that if you want to see this in another form, well, you can look at the radius here, r, and this angle theta, and this tells you that alpha plus I beta is equal to r e to the I theta. And again, this is not a reason why Euler's formula works. That's kind of a different thing. I'm assuming you already know why Euler's formula works. Okay, so we want to look at what happens when the roots of the characteristic equation are complex numbers. And like I said, assuming that the characteristic equation has real coefficients, and which would mean that your original differential equation or recurrence relation has real coefficients, if you have one complex root that's alpha plus I beta, then the other one is just going to be alpha minus I beta, which is always just going to be the reflection across the real axis here. Okay, so let's say that we have a root. We have the two roots, alpha plus or minus I beta. And let's look at the differential equation case first. So, as usual, since we don't have a repeated root, all we do is we say that y is then just going to be an arbitrary constant times e to the first root, which is alpha plus I beta times t, and then another arbitrary constant times e to the second root, alpha minus I beta t. And now the goal is to kind of mess with this a little bit to make it look like a regular real valued function. One of the cool tools we have is, since these are arbitrary constants, we can mess around with them kind of. But anyway, so the first thing we do is we look at these. These both have a common factor, e to the alpha t. So let's take that out. So we take out e to the alpha t, we're left with c1 e to the I beta t plus c2 e to the negative I beta t. Okay, and now it's looking like we can probably apply Euler's formula. So let's look at this. So essentially what we have here is this beta t, we're subbing that in for theta into this formula. And over here, we're subbing negative beta t in for theta. So let's just do that. So this would give you e to the alpha t times c1, we have cosine beta t plus I sine beta t. And over here we have c2 cosine, and now since we're subbing in negative beta t, we have cosine of negative beta t. But since cosine is even, I'm just going to skip a step and say this is just cosine of beta t, because negative signs don't matter with cosine. With sine, however, sine is odd, so what happens is the negative sign could just come out. Okay, so now this is looking a little better. It's looking a little bit more like a real valued function. So what I want to do is just look at these cosines and group those together. So I've got e to the alpha t. How many cosines do I have? Well, I have c1 plus c2 of them. And then how many sines do I have? Well, I have c1i minus c2i. So I'll say c1 minus c2i sine beta t. And at this point, I may as well redefine these arbitrary constants. This one here, I could call this k1, and this part here, including the I could just call that k2. And so what this gives me is e to the alpha t times k1 cosine beta t plus k2 sine beta t. So now it looks like a real valued function, as long as k1 and k2 are real. Okay, but let's take a look at what this solution looks like. So there is a trig identity where you can combine these things into a single cosine or sine. I'm not going to worry about what that is, but importantly, if you're going to draw this as a graph, this just looks like a regular old sinusoid. And then here we see that it has this exponential growth function attached, or it could be an exponential shrink if alpha is negative. So the solution is going to look like this graphically. I can draw like exponential kind of like bounds here, and then what you have is you have this sinusoid going between those. This is just one possible solution, of course. Depending on what K1 and K2 you choose, you could have all sorts of ones, all sorts of different sinusoids, and they could also have different magnitudes, although those magnitudes will always scale up exponentially depending on what alpha is. So let's look at what quantities are involved in this solution to the differential equation. So the root to the characteristic equation was alpha plus or minus I beta, and it looks like, as expected, alpha and beta play a role in the solution. That's kind of a good thing. It would be strange if they didn't. But let's look at what that means on the complex plane here. Well, the real axis has some sort of meaning to it, and the imaginary axis has some sort of meaning to it when we're talking about where our roots to the characteristic equation are. Alpha seems to control the growth rate of the amplitude of the solution. So And alpha, that's the real component. So if we take our root, the further you slide it this way, this would be like exponential growth of amplitude. And if we had it at 0 here, if alpha was 0, then your amplitude would stay constant. It would just depend on K1 and K2. So, and if you went in the other direction, of course, if alpha was negative, then this would be exponential decay of amplitude in the solution. So the real component controls the growth of the amplitude. That's kind of cool. What does beta do? Well, this just changes the frequency of the function. Notice that both of these sinusoids have the same frequency here. So, and again, wherever your root is going to be, the other one is just going to be symmetrical across the real axis. So what you can see here is if beta is close to 0, doesn't matter really if it's positive or negative, but the closer to 0 it gets, the smaller your frequency is going to be, and the bigger that beta is the higher the frequency would be. So, because it would take very little t time to complete a cycle. So, moving up, this would be higher frequency, and then moving down to 0 here, this would be lower frequency. And of course, if you slide up and down this root, the other one is also going to slide up and down in the opposite direction. So it's just a matter of how far you are from the real axis. Further down this way gives you higher frequency. Further up here towards 0 gives you lower frequency. So it'll be interesting to see in the next video how this compares with the recurrence relations that have complex roots. And as it'll turn out, so with the differential equations, what we found is that these two components, real and imaginary, the Cartesian components of this root of the characteristic equation, tell you the amplitude or the growth of the amplitude and the frequency. And as we're going to find with the recurrence relations, is that actually instead of being the two Cartesian coordinates that give you those properties, it's the two polar coordinates that give them. And I think that's pretty interesting. So stay tuned to see an explanation of that in the next video.